In this video, I'm going to be covering how to use an ice table to solve an acid-base type problem. This is going to be a very important video, so please make sure you understand this before moving on to the next section. I'm going to split this into two separate types of problems that we could see. One of them being for a weak acid or base, and the other being a strong acid or base. So in both cases, let's say we have a beaker of water. So we have H2O in our beaker. Okay, now let's say we are working with an acid. So let's say this is our weak acid that we are going to put into the water. And as we know, this is going to form H3O plus and A minus. So when we dissolve our strong acid, which we will also call HA, it will be the same reaction. The only difference is that a strong acid will donate its hydrogen 100% of the time, and a weak acid will not. So we have our beakers. Now, let's say we add 1 molar of concentration of HA into this beaker and 1 molar of HA into this beaker. How does solving these two separate problems differ? So what we can do is we can draw an ice table for this situation. So we have HA, right? And we have this same method over here. So we could literally draw the ice table the same way. So in both cases, we have HA reacting with water, going to hydronium, and A minus, right? And let's put in our states of matter here. So if we were to put this 1 molar in, what are we going to see? Well, in both cases, we will see 1 molar as our initial concentration for our ice table. So one thing we have to note is anytime we see water or any liquid or solid in an ice table, we do not worry about any value for a liquid or a solid. If it is not in our equilibrium expression, we do not need to worry about it. So how do these two problems differ? Well, let's think about a strong acid reacting with water. We know that this hydrogen right here will be donated 100% of the time. We essentially are reacting this acid with water as our base, and we have a whole beaker of water to react with. So there is plentiful amount of base to react with. So this strong acid is going to completely react in this ice table. So this is super important when you are solving a problem having to do with acids and bases. If you are working with a strong acid or base, whatever you start with will completely react and you'll be left with nothing after you react with a base. Or if you're working with a base, they will react 100% and you'll have nothing left. So where did this acid go? Well, we started with 0 molar of this and 0 molar of this in our beaker. Well, we know that 1 molar of our acid reacted completely. So it gave away 1 molar worth of its hydrogens to water. So we must have made plus X, and this is a 1-to-1 ratio. Every time this reaction runs one time, we produce 1 H3O and 1 A minus. So we must have made 1 molar of H3O and 1 molar of A minus. If this was 2 molar, it would have been -2, and this would have been +2 and +2. Basically, for any strong species, you really don't even need to do an ice table. I just like to draw one as a bookkeeping method. When you are solving using a strong acid or base, you just have to know that this will react to completion. So as long as you have enough base to react with your acid, this will react to completion, and you start with 0 and 0 of this. And basically, whatever you use of this, you will make this and this, as it is a 1-to-1 ratio. So how does it differ for a weak acid? Well, we don't have any hydronium to start off. We don't have any A minus to start off. However, weak acids and bases do not react 100% to completion. That is why I emphasize this so much in previous videos, so that when we solve problems using an ice table, we do not make this mistake. We cannot say that this is -1 molar. In fact, it's going to be a lot less than 1 molar. Not a lot of this acid is going to react and give away its hydrogen, because weak acids really don't react anywhere near 100% yield. So all we can say is this is -X. And all we can say is this is +X and +X, because we know we are going to proceed to the products because we have no products at the beginning of this reaction. So all we can say is this is 1 - X, this is X, and this is X. So how do we solve for our concentration at equilibrium? Because for a strong acid, it was quite easy. We already have our equilibrium concentrations of everything. So one really important thing that we need to do when we are working with a weak acid or base, this -X right here. Weak acids and bases barely react. They react so much less than 100% yield. We can call this an approximation, and essentially say that if we start with 1 molar of a weak acid, whatever we react and use up will be so small that it's not even going to affect that 1 molar. It will be so small that 1 minus whatever that number, if you round up using significant figures, is still going to be 1 molar. So what we do is we simply get rid of it. So we make an approximation that because it's weak and it really barely reacts, we can approximate that whatever we lose, 1 molar minus that is still 1 molar. So we can call this 1 molar. And say we are trying to solve for the H3O plus concentration at equilibrium, which we could use to get pH. pH is negative log of H3O. So if the question was asking to find pH, it would be important to be able to solve for the H3O plus concentration at equilibrium. How could we do this? Well, we know that Ka is equal to H3O, which is equal to this entire equilibrium expression. All we need to do is plug in our equilibrium values. Ka equals X, we don't know, X, and 1 molar. Now, all we would need to know is the Ka for this acid, which would be given in this problem. We would need to know that. But if we had this, say it was 1 times 10 to the negative 5, we could solve for X and take the negative log of that, and we would have the hydronium. So knowing the difference between a weak acid-base problem and a strong acid-base problem is very, very important. So I just want to summarize what I did in these two different reactions. So for a weak acid and base, and a strong acid and base. We reacted both of them with water, and we basically saw the same beaker and the same reaction. I drew an ice table. But for the strong one, we really didn't need to draw an ice table or set it equal to any sort of Ka value, because for a strong acid, we know it is going to completely react and go to the product side. That's why whatever we started with, we completely reacted. We are left with 0. Whatever we started with 0, we just made. So solving for a strong acid or base, in my opinion, is much easier because you can just say it goes to completion. Now, with a weak acid or base, we cannot just say it goes to completion. We have to say minus x. We don't really know how much is going to react, plus x, plus x. We approximate that because it's a weak acid or base, weak acids or bases barely react in water because they're weak. We just say 1 molar minus a really small number. When we round it up, is still 1 molar. We can call this 0 plus x, 0 plus x. 0 plus x is simply x. Then we can set this equal to Ka to solve for any concentration we need at equilibrium. And if it were to ask for pH, it would be the negative log of H3O. So being able to use an ice table to solve acid-base problems is going to be very, very important, and something that you can use along the way using these steps.